for you. So I've opened Omics Explorer, our software, and just to show you how it works, I will open an example data set here. What first pops up, this is a synthetic data set. What first pops up is a PCA plot, principal component analysis plot of your data. So this is how it looks like. And Qlucore, our profile is explorative analysis of often high-dimensional data, a lot of visualization to help the scientist or user to explore the data, finding patterns, extracting information. And we have a lot of tools. For example, you can annotate your data, view existing annotations, create new ones. We have annotations for samples and for variables, for example. And we support a lot of features. So this is what it looks like. We have several options of what you can do in the program. You can, for example, show heat maps, view your data as a table, and a lot of other type of plottings. But today's topic is projection score. So we'll start a slideshow here. So, projection score. So what is projection score? It's a tool and a concept to help you select the optimal level of variance filtering for your data sets. Often, for example, in the world of microarray data analysis, you get a lot of information, high-dimensional data. And a peculiar feature of many high-dimensional data sets is that they're often collected with an exploratory aim, without a specific hypothesis in mind. And this means, among other things, that a data set may contain many variables that are not really informative, and the informative structure is hidden in the vast amount of data you have gathered. So what is normally done is that you try to filter your data set, but at the same time as you're filtering, you would like to do the filtering in such a way that you throw away the non-informative part of the data and keep the informative structure in your data set. And what is not needed, and what is needed is something to help you select the optimal projection. How do I optimally filter my data to retain as much information as possible, at the same time as I would like to see it very clearly in, for example, the plots I'm looking at. And in particular, in the case of Qlucore Omics Explorer, we'll talk about the projection score in connection to the PCA projection, PCA plot. And projection score will be a measure of the quality of the projection that you obtain when filtering. In this case, we will talk about variance filtering primarily. So a quick recapitulation of the principal component analysis, just to lay a foundation for the concept of projection score. So principal component analysis deals with the problem of how to project information from a high-dimensional space, for example, 20,000 something variables or even more, down to a lower dimensional space, in this case, a three-dimensional space where you can visualize the sample relations. Projecting the samples onto the principal components, for example, a few uncorrelated latent variables, encoding as much as possible of the variance in the original data. So if you take an analogy, it's like projecting a three-dimensional object onto a two-dimensional screen. And the primary challenge lies in selecting the direction of the projection, so as not to lose, or we want to lose as little information as possible. So in the analogy with the light, you want to position your light source in such a way that as much as possible of the object can be seen on the projection screen. And when you have a lot of variables in high-dimensional data, information in the PCA plot can be hidden by a large number of non-informative variables. And so the common approach is to variance filter, Or, for example, you can have a list of variables that you know are interesting, of course, and you use only those variables, or some other information you have forehand. But primarily in Qlucore Omics Explorer, you can use the variance filtering as a way to reduce the dimensionality of the problem. But in that case, when we do variance filtering, we remove noise from the data set and we expose patterns. But how do we know that we have reached an optimal point? Because if you go past the optimal point, we will start to actually remove the interesting information also from the PCA plot. So we really would like to have a stopping criteria, a quality measure on the projection, so we know when we have reached the most beneficial point for our analysis. So one way to do this, and that's the basis of projection score, is to investigate how does the projection I currently have compared to the projection that I would get if the data would be completely random. So this is where projection score comes in. So as I said, projection score will be, in that case, the difference between the variance observed in the data set compared to the expected variance in a data set of the same size consisting of completely random variables. And I just put up some formulas here. I will refer to a publication later where you have the complete mathematical foundation for projection score. But just as a reference, we can see that, or if we define alpha as to the lower left here, and that is essentially the fraction of the variance that is contained in the PCA plot after filtering. And then we define the projection score as to the right, where we have the alpha, the fraction of the variance observed in the data set, and we subtract the variance we would observe for the same setting for a set of completely random variables, a data set of the same size but consists of completely random variables. What fraction of variance will we get then? And if you take this difference, that will be a measure on how good our projection actually is. That's the basis for projection score. Yeah, let's go back here. Yeah, and this, the second term in the difference will actually be the average of a lot of randomization. We will iterate commutes until we get a null distribution, and from that null distribution we extract the average value, and that will be this second term in the projection score. And of course, calculating the projection score requires extensive simulations on random data sets. If we would like to, we commute variables and we draw from the from the random distribution. But then you would lose the interactivity. And one of the main parts of Qlucore Omics Explorer is that the analysis for most parts is completely interactive. You have a slider, you drag the slider, and you see immediately the change in your data. And in order to retain that feature in the program, we have decided to use a pre-calculated sort of surface where you have a lot of, if you see in the plot here, we have dimensions for the samples and for the variables. And we assume a normal distribution, and we pre-calculate this null distributions for a lot of combination of sizes for samples and variables. And of course, this will not be the exact projection score, since most data is not really normally distributed. But as we will see, it will give a fairly good, or in many cases, a very good approximation to the correct projection score. And if one would like to, we can then later go on to do the full simulation, extracting the real projection score. But as we'll see, as a rule of thumb, this will give us a very good result. And it will have the benefit of retaining interactivity, so that the initial explorative analysis will be very quick. You can drag the slider and you can see, okay, there's my optimal stopping point, and from this point I can start to work and refine my research. So, as I said, projection score has a very firm mathematical foundation and a rationale. And for further reading, we refer to this article by Magnus Fontes and Charlotte Sonesson. It's called Projection Score, an evaluation criterion for variable subset selection in PCA visualization in bioinformatics. It's free available on the net, and here you have the link to the article. I just keep it here a minute for reference, but if you would like to look it up later, if you have Qlucore Omics Explorer, you can simply go to the reference manual, search for projection score, and we will have a short recap of the projection score and also the link to this article. Yeah. So we will go on to show a few examples of how projection score is applied in Qlucore Omics Explorer. So now we have the program here, and I will start by looking at a real data set, an acute lymphoblastic leukemia data set. This is a real data. And the first thing you get is the PCA plot. I'll select the annotation leukemia subtype. I will color according to that annotation. So here we have, to the left, we see the different subtypes of leukemia, and we have colored the PCA plot according to this. So now, when we start out, we have, you can see in the lower left corner, 132 samples and 22,000 something variables. This is a lot of variables, a lot of information, and in order to reduce the dimensionality of the problem, I will start variance filtering our data. I bring up the statistics window, and here we have a slider for filtering by variance. So what will happen when I filter by variance is I will start removing the variables with a variance lower than the set value. And to the right of the variance slider, we have a small box, currently green, with a number in it, and this is the projection score calculated for this data set with the current settings, number of variables, samples, etc., and based on this pre-calculated null distribution for the data set. So, and also I should say that we have chosen to color the projection score box with green for a good, very good score, yellow for a little bit less good score, and red for a bad projection score. And the limits for these colors is based on our experience, mainly from microarray data, what should be a good projection score. And of course, if you have other types of data, the colors might not exactly match. I mean, a yellow could be good or bad, but still, it would be a relative measure if you use the number itself to determine an optimal point. But the colors are there, and they are a fairly good approximation, as you say, and an indicator of how good your projection is. So now I will start by filtering by variance. So we see that initially we have a green light, and it's quite a high value. And as I continue to filter, now things start to happen when I go under a certain level of variance. And you can see it's still green, and if you look at the lower left corner, we have like 21,000 variables left. If I continue to drag the slider, now the box starts to get yellow, the projection score gets lower and lower. And now we are again approaching a green box and a higher projection score, 0.33, and as I continue to drag, it will go down again until it becomes red. So I will go back to this point. Here I have 265 variables left, and we can see also in the plot that the data is starting to group really nicely. If I choose select the first, I had green lights in the beginning of my dragging of variance slider. We can see we have a lot of noise in our data. There is no real structure in the data, so this indicates that although we have quite a high projection score, it's actually very difficult to see any patterns in data here. But as we continue to filter, we see that on the next maximum in the projection score, we have a good grouping here. So this is a nice example of this data set. We have two maximums, and between them we are filtering out a lot of non-informative variables. So, and we also see that the magnitude of the variables left corresponds very well to the number of variables contributing to the leukemia. To the leukemia. That should be around 100 or so. So now when we have reached this point, we would like to do some, for example, some statistical tests. We can, for example, do a two-group analysis on something, and we start filtering on p-value. And we see as soon as we start to filter on something else on variance, the projection score box becomes gray. That is because as we have implemented projection score, we are basing it on variance filtering. Of course, you couldn't base it on other measures, but that will require different sort of calculations for the null distributions, etc. And variance filtering is often the initial, it's a starting point for analysis, and that's where you would like to do the coarse filtering and get an optimal stopping point. And from there on, you can start refining your analysis. So that was a real-world data set, and you can see the effect here. As I said, it's actually, if you would plot the projection score as you drag the variance slider, it would be a fairly smooth curve with two maximums, and between them you will filter out a lot of randomness in your data. You retain the informative structure. Just as a counterexample, I would like to open a random data set. You can generate it from the Qlucore Omics Explorer. We say 1,000 variables, 100 samples, and here we have it. This is a random data set. So you have to see the contrast here. If you have a completely random data set and you start to variance filtering, soon something starts to happen. Here we start to filter out variables. But we see that all the time projection score is 0. And that is because as we define projection score, take the fraction of the variance and we subtract the fraction of variance for a completely random data set. And of course we have two completely random data sets in this case, and the difference will be 0. So no matter how much we're filtering, we will still have no structure in our data. This is a projection score of 0, close to 0. So I think that concludes the introduction to the concept of projection score as used in Qlucore Omics Explorer. As I said, the article contains the mathematical foundations and further information on examples where people have used projection score to obtain optimal filtering. So, do we have any questions? No? In that case, I will, for future information, refer you to the website, qlucore.com.